Hello and welcome back to the CCENT journey with me, Ryan. In this next section, we'll continue looking at the Open System Interconnect model, starting with the network layer and working down towards the physical. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. Okay, so moving on, we're going to continue our discussion on the lower layers. As I previously mentioned, the lower layers are actually the transport, network, data link, physical, and the upper layers is the session, presentation, and application. In our previous video, we discussed application, presentation, session, and transport. And we're going to start here by talking about the network. Before I do so, quick review. The application layer, this is where applications like FTP, the file transfer protocol, HTTP, the hypertext transfer protocol, SMTP, the simple mail transfer protocol, and other things like Telnet, SSH, POP3, many applications. This is where they all sit. This is where the networking applications interact with the network. This is essentially where our end users sit. Depending on what application they're using and how the application should be presented, maybe for example it has JPEG, so it has a bunch of pictures. Maybe it needs to be compressed to save on overhead as it passes across the network, or maybe it needs to be encrypted because it's some important file. However, that information needs to be presented. That's done by the presentation layer. We then move into a discussion around the session and transport layer. It's important to understand that these work very closely with one another, and just like any layer to an extent within the OSI model, not every layer needs to be used. A good example of that is between the transport and session layer. Depending on the application, the session layer may not reserve the ports. It may actually rely on the transport layer to do so. And we also discussed that the session layer is where the duplexing takes place. So if we had a PC that connected to a remote server, there would be a negotiation to determine whether this particular server and this particular host can communicate in full or half duplex. We then had a brief discussion around how the sessions are actually unique, using the ephemeral port as a random source value, and 9 out of 10 times, depending on the application, we sometimes see at the transport layer something called a well-known port. And we discussed a few of the well-known ports, and as I previously said, it's very important that when you go through understanding the well-known ports, that you memorize the ones that are outlined in the text that you're reading to pass the CCENT. Okay, moving on to the first layer that we're going to discuss in this video is the network layer. So the PDU for the network layer is called a packet. It's important to remember. The same way it's important to remember the PDU for the transport is segment, and for all the ones that we've discussed above the transport layer is OR data. We also here come across our first bit of hardware that's important to mention that runs at a particular layer within the OSI model, and that's a router. So this is an example of hardware. You may also come across a switch which runs at layer 3. For those who are not sure about this, I'll come onto this a lot later when I discuss the difference between a layer 3 switch, a multi-layer switch, a content switch, and so forth. For now, understand that it is possible that switches to run at layer 3, even though the majority of them will actually run at layer 2. We also come across a protocol called IP. IP itself can be split into many different versions. We have IPv4. We also have IPv6, and other protocols that run at network layer include the IPX or something called Appletalk. Depending on the protocol running, in this case, let's say for example IPv4, we have an IP address. The IP address is essentially the address of a particular PC, host, or device like a router and sometimes a switch. To give an example of what the network layer actually does, it can do two things. You hear something called a rooted protocol and something called a routing protocol. So a rooted protocol is what we've discussed already. So that's your IPv4, your IPv6, your Appletalk and so forth. A routing protocol is used to actually route traffic. So to give you an example, if we have a think about what we discussed earlier. So we had a PC and our PC was attached, let's say, to a router. Remember, this is a symbol for router. And let's say we have a single link out to the internet, and off the back of the internet, let's say we connect them to another router, and let's say another router again, why not? And then we have a server. And this particular host would like to communicate with this particular server. What would happen is routing will ensure that when he or she requests traffic from this web server, let's say for example it's 192.168.1.1, essentially when it creates that data, so remember we had the data from the upper layers, and then we had the TCP, which had a source port, let's give it an ephemeral port of, let's say, 3033, and a destination port, let's give it a well-known port of port 80. We'd also have an IP header that goes on top of that, and the IP will have the destination of this IP and the source of this IP, and essentially this will allow each router, even if there are multiple routers in the internet that connects together, each router will have a look at this information and know how to get to the particular destination. And the reason it would know how to get to the particular destination is because each of these routers will communicate together using a routing protocol, some of which are called OSPF, RIP, BGP, EIGRP, and many others. And essentially these are languages that these routers speak to one another to advertise what IPs it knows about. So this particular router knows if I want to get to 192.168.1.1, pass it to this guy knows to pass it to this guy knows to pass it to this guy, and so forth until it reaches essentially the destination IP address. Okay, so moving on to the second from last, it's actually our layer 2, which is called a frame for the PDU. We have another bit of hardware that runs here, and that's a switch. I did mention just a moment ago that switches can also run at layer 3, but for now they primarily run at layer 2, and let's believe that until we get later into our studies. An example of a protocol that runs at data link layer is most popularly known as Ethernet, but there are other protocols like PPP, HDLC, and we also have protocols like PPP-OA and PPP-OE, which is used to actually deliver digital subscriber line technology, which essentially is your broadband. If, for example, it uses Ethernet, it's going to use this thing called a MAC address, which is a media access control. A MAC address may be called a burned-in address, hardware address, or physical address. But for now, let's go and keep it as a MAC address. Every single NIC, whether that NIC is part of a server, whether it's a tablet on a handheld device, or whether it's a personal computer, regardless of what it is, every NIC has a MAC address, and hopefully that MAC address is globally unique. The reason it's globally unique is because there is this MAC address here is actually 48 bits long, so that actually essentially means 101010 48 times. If you turn that into hexadecimal, it will actually come up to an average MAC address, and out of those 48 48 bits, there's actually 24 of them are reserved for something called the OUI, which is the Organizational Unique Identifier, and each vendor is assigned a Organizational Unique Identifier. And when they're assigned this unique identifier, it allows you to look at a MAC address, for example, like this one here, and using half of it, able to identify what vendor actually created that NIC card. A good way to think about the differences between the network and data link layer is the network layer is primarily used for communication when the device is not on the same segment, and the data link layer is primarily used when the communication is on the same segment. Okay, so just outlining what I just said around the layer 2 and layer 3 communication, I said that layer 3 is primarily used between segments and layer 2 is primarily used within segments. I just want to touch base on that before I confuse anyone. If you think about a PC, and our PC is connected to a router which goes off to another router which connects in to the server. Ultimately, this PC is trying to communicate with this server. Both of them will have an IP address. Let's say, for example, this server has 172.16.0.1, and this particular PC has 192.168.0.1. When they go ahead and create their packet, let's say that this particular PC is doing a HTTP GET message. So it's trying to download a HTML page from this web server over here. Therefore, its HTTP GET is put together with the help of the layer 7 application layer, the layer 6 presentation layer, and layer 5 session layer. It then works with TCP to populate the TCP header, and it works with IP to populate the IP header, and then ultimately there's the frame is created, populated in this case with an Ethernet header and Ethernet trailer. So this is your layer 4, layer 3, layer 2, and then as it goes across the wire, as it's ones and zeros, this is where our layer 1 sits. Now, initially what I meant by IP between segments and Ethernet within segments is each one of these here is actually a segment. These segments are sometimes referred to as segments, they're sometimes referred to as broadcast domains, and they're also sometimes referred to as networks. And essentially what happens is as communication passes between networks, the destination and source IP remains the same until it gets to the destination, but the Ethernet header will change on a per hop basis. So if you think about in the IP header itself, if we blew that up and look inside, we'd have a destination of 172.16.0.1, and we'll have a source of 192.168.0.1. Now throughout each of these hops, if you like, the source and destination IP is not changed. The only time this is changed is a couple of reasons. One, if one of these devices is using something called NAT, which is network address translation, and this is not going to be the case for this scenario. Or two, it does reach the destination, and when the destination needs to send traffic back, it actually swaps the destination and source around and sends the data back, which in this case is going to be the HTTP response to the GET message. Now, as this PC sends it out, assuming that the destination is always 172.16.0.1, what we need is some sort of communication between this PC and this router, and then between this router, and then ultimately from this router to this server. And this is where the layer 2 header, or the data link, comes in handy. It uses its own addressing. In this case, remember we mentioned it called a MAC address, which is a media access control address, and we said it was the 48-bit address, as opposed of a layer 3 address, which is a 32-bit. Essentially what would happen is this layer 2 frame will have a destination of this particular router, and when this comes in to this router, the router will take the layer 2 frame off, as the actual frame itself was for this router. The router will then look at the next layer up, which is IP, realize the destination is actually not for itself, but it is aware of the communication, it is aware of the location of the 172.16.01 through the routing protocols. So remember I said that this is things like the OSPF, this is RIP, this is EIGRP, and because of that it knows to send it this way. But before it sends it this way, it needs to populate and create a new Ethernet header and Ethernet trailer. So it populates the Ethernet header with the destination as the next hop, the source as itself, a new frame check sequence to help it traverse across the cable, and when it reaches the other side, again the router will strip off the Ethernet header because the destination was for itself and the MAC address was destined for this device. It will realize actually it's not for this device because the IP again is not on this actual router, it's actually out this link, and therefore the router will essentially create another layer 2 header, another layer 2 trailer, but this time the MAC address of the server. It will send it out to the server again will receive the frame in, see the Ethernet header, take the Ethernet header off, see the IP, realize the IP is the web server, which means it's reached its destination, and then only then will the web server actually take off the IP header, look at TCP and realize that it's a HTTP GET request because it's running on port 80, and then push it up to essentially the HTTP application. The HTTP application will respond and the traffic will continue back using that encapsulation and decapsulation process between the layer 2 and layer 3 MAC address and IP address, again keeping the IPs essentially the same unless it goes through a NAT device. But what it would do is, instead of being the destination of 172, because it's going back, this will actually be now the source, and the source will essentially become the destination, and each router will receive it in, take the Ethernet header off, know how to get back to 192.168.0.1 out this way, and continue forth until again the response arrives at the originating host. Now I appreciate that may have been a little bit off course, but it was key for me to keep that in there to give you a bit of a taste essentially of how the network and data link layers work together to achieve end-to-end communication across multiple hops. It also gave you an understanding of what I meant when I said the IPs are primarily used between segments and the data link is primarily used within the segment. Later on, when we dive into actually how Ethernet communication works and how other layer 2 protocols work, we'll start to understand how that communication path actually is created using protocols like the address resolution protocol, and also what would happen if we had other layer 2 protocols running at the data link layer like PPP, and how they communicate, because those types of protocols do not have MAC addresses. Last but not least is the physical layer, layer 1. Physical layer is essentially the bits. It's sometimes referred to as cells, but primarily it's referred to as bits. So when we think of a PDU, we call it a bit. We still have devices that run at layer 1. In this case we have a hub. I previously mentioned a hub itself has a very basic symbol, and all devices plugged into a hub, when it sends traffic in, the hub purely sees it as electrical signals and sends out of or the attached links, and this is why a hub is sometimes called a repeater. We also have our cables here. So we have our copper cable in, and we have fiber cable in, and we also ironically have at the physical layer wireless. The physical layer also measures things like the voltage, the mechanical procedures required to actually transfer information across the wire itself, and the actual voltage charges, the physical data rates, the maximum transmission distance, and what the physical connectors actually are. So I've mentioned in a previous video things like the RJ11 heads, RJ45s, and things like the straight tips when we talk about fiber and other ports. Okay, so that's all we've got time for during this lesson. Just to confirm, we've done a review of the previous layers. We talked about the application, the presentation and session layer. We had a discussion around networking. We talked about the difference between rooted protocols and routing protocols. We said that the rooted protocol are things like IPv4, IPv6, Appletalk, and we said routing protocols are things like RIP, OSPF, EIGRP, which is the routing information protocol, and the open shortest path first protocol, and the enhanced interior gateway routing protocol. And we said that these particular protocols are what routers use to talk to one another, to essentially inform and to learn about how to reach particular destinations. And because the destinations that we're talking about are at the network layer, it means we're talking about IP addressing. We then moved on to the data link layer. We had a discussion around the communication that happens at the data link layer. We said that some of the protocols here are things like Ethernet, PPP, HDLC, and then I had a very quick overview around how the data link and network layer works together to essentially have traffic to go across multiple hops to reach the destination. As I previously said, we're going to a lot more depth as we go through our course. I wanted to give you a demonstration of how these two actual layers work together in order to get end-to-end communication. Lastly, we had a conversation around the physical element. I said this is where the mechanical, electrical procedures take place. Essentially, this is where the specification defines things like voltage levels, timing of voltage changes, the physical data rate, the maximum transmission distances, and this is also where the physical connectors live. So when we're actually talking about copper cabling, and the ends of the copper cabling, RJ11, RJ45 and so forth, and when we talk about fiber, we're primarily talking about layer 1 attributes. We also said, ironically, this is where wireless lives. Last but not least, I want to thank you for viewing, and I hope this has been informative, and if it has been, please do like and subscribe.